Thanks, Greg. Can people hear me? Apologies for my voice. I've got a virus sitting down in there. Can you hear me at the back? Yeah, thank you. Okay, well, it's pretty cheeky for a Kiwi to be up here talking about eucalypts, and I'm well aware that I might take a beating, particularly since I didn't even know there was a eucalypt called Smith until about 3 months ago, and had to go and get Dr. Google to help me out. But there was a reason for giving this talk, and that is that we've been working with our colleagues at Seed Energy, and it seemed like a good opportunity for us to, Sue and I, that is, to, if you like, build that collaboration with them. And so, as you'll see, Steve Smith, Mike Bird, Peter Gore all here, Barry Vaughan, of course, is here. Did I do that? Okay, back again. And as well as that, Neville Jobson of Abacus Bio, he's not here, but he helped with the analysis, and some of you will have met Luke Proctor, who's from that same organisation with Neville. And of course, it was a pleasure to renew collaboration with Joe Sass, who's somewhere here, I think. So plenty of people to keep me honest. And really, I'm mostly talking about, as you'll see, other people's work. So in preparing for this, I had this real inspiration for this new concept called species in waiting. And then, of course, it wasn't too long after that I realised that Chris and Nambia and others had already beaten me to it. And they came up with this concept, which I rather liked. And I'm sure it was, and Chris can confirm, I'm sure it was driven from their experience with the acacias in Southeast Asia and the Ceratocystis problem, and the fact that they had to move quite quickly into looking at some other species, other acacias, and of course Eucalyptus pallata. But I think it also sort of speaks to a more general issue in tree breeding, that we have to put in the resources and the time and the energy to have these species prepared for plantation use. It's not enough just to talk about the genetic resources we've got out there. As breeders, we really have to essentially engineer the species up to the stage where it can meet the expectations of growers. And I'm sure that was in Chris's mind, and Nambia and their co-author. And also risk management. Again, it's bad enough having, as we do with growing exotics, we lose our exotic advantage over time. Heidi mentioned earlier the erosion of, well, not even the erosion, really, the problem in New Zealand of not being able to grow eucalypts, because every 3 months we get either a pest or a disease that likes to eat them. And so, you know, it's been a bit of a lost cause. And even our radiata pine in New Zealand, over time, we're starting to see more diseases and pests come from elsewhere and just start to wear away at the species. So we've got risks with the species, our major species that we have to deal with, and climate change, of course, is looking like exacerbating those risks. So the eucalypt called Smith, Eucalyptus smithii, which Seed Energy and others have been working with, and also STBA. A little bit of information about it. Its distribution here. It's got a lot of pseudonyms. Northern Victoria, southern US, southern New South Wales, and either a mallee or a tree form growth habit. Natural distribution, pretty good range of altitude it grows across, reasonable range of temperatures, some useful resistance to frost in there, and again, ability to grow across quite a range of rainfall, and apparently similar response to drought as globulus. Grown quite extensively, I understand, in South Africa, and Xander can no doubt correct me if that's not correct, but SAPI have obviously done a lot of work with it. Here's what they found. Again, not too surprising, summer rainfall area, reasonable amount of rain and good temperature range, good coppicing ability, and in South Africa apparently the essential oils market is of interest as well as the pulpwood market. As far as pulpwood goes, they've published some work that suggests that it's an excellent pulping species and can be grown on a relatively short rotation. So in Australia, Hancock's started some years ago with essentially a progeny trial seedling seed orchard planting that had a lot of families from near Talaganda and some other provenances represented there as well. They planted it out in a individual tree design so that it could be thinned to a seedling seed orchard, and they had some controls in there. And with the age 14 results, Joe was able to analyse them and came to some conclusions about the trial. Quite respectable growth rates for age 14, 15 metres average height, 15 centimetres diameter. Apparently on that site, better than globulus, and good survival as well. And on that site, the Toowoomba and Mount Dromedary provenances appeared to be generally the best for growth and form. Joe commented on the fact that there was a heritability for diameter and volume, but she suggested that perhaps measurement at an earlier age might have yielded a higher heritability. And I'll come back to that point. So in 2012, Seed Energy, not quite sure of the individuals involved, we've done a little bit of digging back, but Seed Energy and others established a trial quite close here to where we are now. And in this case, unfortunately, there wasn't much overlap with the earlier one. There were 5 individual tree seed lots from the earlier trial, and we hadn't been able to track them back. So we weren't able to look at things like release from inbreeding that we might have otherwise liked to have examined. But a wider set of provenances tested in that trial and assessed at age 6 last year for diameter at breast height, and pyrrolidine as an indicator of density. The results are here. On the diagonals, you've got some fairly respectable heritabilities, genetic correlations down here, phenotypic up here, and overall means over here. And just to point to the pyrrolidine correlations with growth, positive in this case actually means negative in terms of wood density. So their results, and they've only just been in a few days, those results, so these are preliminary conclusions. I have the breeding values, but I won't be showing them here. But in general terms, on this site, which I think is about 800 millimetres rainfall, Steve mentioned to me, not a fast-growing site, but a good performance there. And again, the Mount Dromedary provenance came through along with Ben Boyd and Kadji. These will mean something to some of the locals. A useful heritability, I would say, for growth and density improvement, but obviously that negative correlation to deal with. And the first seed is becoming available from that seedling seed orchard, which can now, of course, be thinned based on these progeny trial results. So perhaps the question, does it qualify as a species in waiting? Well, maybe it does. In terms of potential in Australia, there's still a need for new plantations. The species apparently does have reasonable tolerance to pests, similar range to night hens, but perhaps with a bit more frost tolerance. And Bragg gave us some criteria for climate change. I think that was yesterday, and as it happens, you can tick the box for Smithy eye, high density, thick bark, and it does form lignotubers. So, bit of resilience there. Now, the tree breeders have seen these things before, and some of the others will have as well, and really this is just to make the point that as tree breeders we need time in which to, work with the genetic diversity, carry out our selection, manage our breeding populations, package things up into seed orchards or some form of propagation so that we can deliver high gain deployed material, whether it be clones, families, open pollinated, control pollinated, whatever. And essentially, it's easy to pick the winners. The market has already done that for us, and so you've got between SCBA, Seed Energy, you've got well-managed breeding populations of these three species. But really, we're talking about a situation where, if you think about these as those species, and if you think about the sea of sand as the massive amount of genetic diversity that we've been told about at this conference in the Eucalypt taxa, then somehow or other we've got to be building these new pyramids and getting them ready for eventualities. Otherwise we'll be left with the level of gain down here. And Xander, I think, gave us a challenge at the beginning of this conference in 20 years' time, what we hope to have achieved. And I think one of the things to achieve will be to try and speed the process from, if you like, from the gene resource up into the packaged breeding population. So the species in waiting, you'll notice that the breeding population has dropped out. Essentially, there's a production population, which is the seedling seed orchard. The resources aren't available for these species and others to do the full-blooded breeding program, so the breeders are doing what they can to get material that is pre-packaged and ready for deployment should the need arise. Further down the list, there's a longer list of less intensively managed species, again without the ability to do much breeding, and in fact not a great deal of resources to spend on the production population as well. So these are the problems that we face with these species, and as Peter Gore reminded me yesterday, that it's the art of responding to the market signals and to the climate signals, I guess, as well, and knowing, where do you look within the resource to determine which one's the next. So I've only got, a couple of conclusions, fairly obvious ones. Smithii, I think, is shown to be another promising plantation species. There's a niche here in Australia. There's a probable niche internationally as well. Others will know that better than I. And it's just one of a promising species from within this really remarkable wealth of genetic resources that you're dealing with here in Australia. So, as I mentioned, developing these species, identifying the species in waiting and then developing them and getting them into a kind of a pre-deployment state is still a major challenge, and really there's not a lot of resources available for this. Some of you know this very well. A lot of it is based on the passion of a few individuals spending their own money in many cases to set up the situation. So, if there is a way of getting more funding into this area and getting more research into how to do this more quickly, I think we need it. And that's the last question, really. It's a rhetorical question for all of you here. Given the likelihood of climate change, the erosion of the advantages we've already got, particularly with exotics, how are we going to translate this hugely valuable resource into material that we can actually use and sell to the TMOs and the REITs, who basically don't give a stuff about tree improvement anyway, and convince them that these things are worth investing in. And that's it. Thank you.
Thanks, Mike. He's given us a good description of what happens in those sort of between the really actively managed breeding populations like globulus and the conservation and stuff at the top. What are we doing in the middle? Thank you very much. Any questions for Mike?
More of a comment, Mike. I think one of the things we have to look at with these species in waiting is what they're going to be used for. The demand will always be greater if there's a commercial product in view. And as we go to the drier climates in Australia, it's not so. It starts to get more difficult to use the wood for pulp. You're further from the pulp mills, and also the wood is less suitable. So I think part of what we have to do is to develop new products, such as like they're doing in New Zealand with the Vineyard Post Initiative, terrific, and probably rotary veneering as well. So as well as thinking about the biology, we have to think about the market use for the wood. Yes. Just a comment.
Yeah, agreed, Chris. Yep.
Okay, thanks again. Our next speaker is Gary Hodge, so eventually we'll get some Australians talking about eucalypts, but Gary's got a lot of experience and no doubt he'll give us a good story.
Thanks, Greg. So I direct a program called CAMCOR. If you've never heard of CAMCOR before, I need to give you maybe a little bit of background. Part of North Carolina State University, and CAMCOR is a university forest industry cooperative research program. Our focus and our mission is on genetic conservation and genetic diversity in forest trees and tree improvement. We are 39 years old this year, and currently we work with 26 forest industries around the world. The vast majority of those are in the southern hemisphere. If you've heard of CAMCOR before, then you're probably thinking pines and wondering why is this guy here talking about eucalypts. And our history is indeed with pines. That's where we began, with subtropical pines of Central America and Mexico. And we have lots and lots of exciting things happening in our pine testing and breeding programs that I can't talk about today, but I'll talk about if you want to come ask me questions. But over the last 20 years of our history, we've been working more and more with eucalyptus. Nearly all of our members grow eucalypts. Some of them only grow eucalypts and they don't grow pines anymore, but nearly all of them do grow eucs. And we began in 1997 making Eucalyptus Europhila collections in Indonesia, and we have a very large population of Europhila. But we have family level, at least modest size, family level collections of 15 eucalyptus species. And we want those to be able to offer those to our members, whoever they are and wherever they are in the world, to have some options with these particular species and at least get them started and have that genetic diversity available. In the CAMCOR program, every member owns everything. Okay, so even if it's not on your land today, you have access to it. And so the fact that we have this together is a valuable genetic resource. And we want to expand that even further. So last year we contracted with Jacob, working under the direction of Brad, to do a literature survey for us to identify some new species that we might be interested in collecting over the next decade. And our goals were to think about species that offer some adaptation to relatively challenging environments that some of our members face in certain regions, or that offer some interesting wood properties or disease tolerance, etc. Okay? And the reason that we're interested in such a range of diversity is because we're very interested in eucalyptus hybrids. A lot of our members are using hybrids operationally now. Brad mentioned yesterday the importance of eucalypt hybrids in terms of adaptation in the natural environment. And we think it's even more important when you're talking about taking eucs to exotic environments, that you need to have hybridization options. We have 2 hybrid breeding programs or breeding projects within our membership that are underway already. In the first one, we're starting to propagate a small number of clones of about 10 different hybrids. And in the second phase, we're just now starting some crossing for about 25 new hybrid combinations. And you can see that we're pretty high-tech in CAMCOR. And so we're not far behind all you folks who are using Oxford nanopore stuff as well. So we're right on your trail. So with that as a background, I want to talk to you about why we're doing that. That should give you some idea why we're doing this relatively applied research project of looking at the wood properties of these species. When we talk to forest managers or forestry vice presidents and you say, well, we've got this new species in waiting, this new alternative species that shows a lot of potential on your land, either as a pure species or a hybrid partner, they say, that's nice. What do you know about the wood properties? Okay, because the first thing they want to know is, what about the wood properties? Because they're making real products. And so it's important to demonstrate to them on their lands, okay, what are the wood properties of these species, okay, so that they can decide whether or not they want to invest resources in it going forward. And so that leads us to this study. This will be an ongoing study. We're probably going to continue to do this work on other sites for the next 5 or 8 years. But what we have today are samples of species trials that we've planted on 3 different locations, in Chile, in Uruguay, and in South Africa. You can see the information there about the sites. But what's important is that on each of these, there's like 2 different species trials that we've analyzed, sampled together with an array of species. And the other thing that's nice about this data set is that these 3 environmental zones each have a different primary commercial species. So in Chile, it's globulus with a little bit of nitens. In Uruguay, it's dunny with maybe a little bit of grandis. And in this location in South Africa, which is in Limpopo province in the northeast side of the country, it's Eucalyptus grandis. That's the commercial species. So what we do is sample some solid wood properties using acoustic wave velocity on the standing stems to measure modulus of elasticity, which is a measure of timber strength. Okay. Basically, it's a function of microfibril angle when you're talking about green stems. If it was dry saw timber or dry logs, then it would be density and microfibril angle. But in this case, it's MFA. But we're going to call it green modulus of elasticity. The second trait is a density-related trait, which we measure with the IML resistograph. This is a motorized precision drill. Pushes a very small drill bit through the stem, creates this sort of trace, set of information. And you can look at that trace. This is a pine sample, but you can see the annual rings. You can see some little lumps over here, which are related to the bark. And you can see some flat lines at the very, very beginning and at the end, which is when the needle has passed out of the tree. And you can see a tendency for the friction or the resistance to increase as that needle goes through the tree. Okay? And we use an R code to clean up that data that identifies when the needle has come out of the tree, then flattens that profile, then identifies a transition area for the wood, and then says, okay, everything above that line is wood, and that mean resistance then is linearly related to density. So we call it density, or you can call it resistance. Okay, but basically we're thinking density there. And then we also take wood shavings at breast height using a hand drill, collect the shavings, bring them back to North Carolina, grind them up, use NIR spectroscopy to predict glucose and xylose and lignin and SG ratios. So that's lignin composition, that's the syringyl-guaiacyl ratio. We use a slightly different formulation of that variable because we get better NIR models and we get better heritabilities using that expression of the trait. But you can think of it as SG. Okay. Oh, and maybe one other explanation. The syringyl form of the lignin is the one that's easier to extract, so you want higher SG ratios if you're a pulp producer. All right. The data analysis is pretty straightforward and pretty simple. Just an analysis of variance, calculate least squares, means, and standard errors, and then we compare them. So now we're going to look at results. Every one of the following graphs has a constant color for a species from graph to graph. So you can pick your favorite species and look for that color. I've highlighted the commercial species, okay, for easy comparison of the others. So in this case, it's globulus and an open star for nitens, which is also a commercial species in Chile. And so we can see globulus has nice glucose. If you're a pulp producer, then that's a good thing. It has extremely low lignin, which is also a good thing. And it has outstanding lignin composition, so a very, very high SG ratio. So that's great. Globulus is really good. Nitens, low glucose compared to globulus. Okay? A little bit higher lignin, but not too bad compared to some of the others. The lignin composition is okay. And this is kind of interesting, I think, is that the nitens picks up a lot of xylose. Okay? So it's not creating as much glucose, it's pumping out a lot more xylose. Okay? So now with that as a background, where's Mike's new species in waiting, Eucalyptus smithii? There it is there. So sort of intermediate on the glucose level. It's got very nice lignin content. It's got very good lignin composition, so that's all good. And then here it is. It's got a little bit comparable xylose to the globulus. Okay, so that's a good one. I also want to comment on Eucalyptus benthami or benthami. This is an interesting species. A lot of our members are interested in it. It's very rugged. It can grow well in rather hot and humid environments. It can tolerate also very cold and frosty environments. So it's very interesting from that standpoint. The wood quality, though, is not so good. Okay, so the glucose isn't too bad compared to globulus, but it's got a lot of lignin. It's got bad lignin. Okay, and then if we look at density, where is it? There it is there. It's at the bottom of the list in terms of density, and it's not very strong. So it's got a low MOE. Right? So that's a little bit disappointing because a lot of our folks were really interested in benthami. It's good. Is that 5 minutes? Oh my goodness. We're fine. No worries. Now let's go to Uruguay. So we got Dunnii and grandis are our commercial species. Good glucose, good lignin, relatively good for Dunnii, good lignin composition. So Dunnii is a nice one. Okay. Let's look at. Let's not look at benthami because it's bad here as well. Let's look at these two, Corymbia maculata and Corymbia citriodora. That's citriodora citriodora. Okay, so pretty good glucose compared to grandis and Dunnii. Much better lignin and better lignin composition than grandis. Not quite as good as Dunnii. Okay, it's also producing. These two are producing a lot of xylose. Okay, and if we look at resistance and density for these two, okay. Here's the commercial species, here's maculata and citriodora citriodora, and also in terms of MOE. So that's kind of interesting. And if we go to South Africa, there's our commercial species grandis, benthami again, bad, bad, bad. Okay, so it grows, it survives, it'll produce a crop on a harsh site, but it's not going to be one that you want to put all your money into. Pelita and Europhylla, which the South Africans are using for hybrids and for add some drought tolerance and some pest resistance. You're going to take a hit compared to grandis in terms of glucose. You're going to take a hit on the lignin. There's a lot of lignin in Pelita, and there's the Europhylla. And the lignin is not very good. Okay, so it's down here at the lower end of the Eucalyptus grandis. So the Corymbias, good, good, good. Right? And if we look at resistance and density for Corymbias compared to the grandis, good density and pretty good MOEs. Okay? So the next 3 slides are the same data, but I'm trying to put all of the traits on the chart at one time. So we'll see if it works. You got density, MOE on that axis. The size of the bubble is the glucose content, so the bigger ones are more glucose. And then the little wedge shape here is the guaiacyl lignin. You want that to be a skinny wedge. That's a little bit hard to see on these charts, but globulus you can see is well above. It's got a big bubble and it's got a relatively skinny wedge, at least compared to some of the other species. So globulus is a winner again, which we had seen. We go to Uruguay. These are our commercial species, Dunnii and grandis. Smithii. Remember, it has more xylose, okay, so it's a little low on glucose, but it's making up perhaps with some xylose. It's got good chemical composition, and here's the Corymbias. And the last one is here in South Africa. Here's our commercial species. Here's the 2 Corymbias. Pelita, which is one of the alternates, it's got some density and some MOE, but that's bad chemistry. Look at that guaiacyl. The Corymbias look pretty good. And then these 2 funny dryland species with incredibly high densities and MOEs, but they don't grow very fast. So we'll have to think about those. So in conclusion, The Corymbias look really good. High density, good MOE, low lignin, high SG ratios, and they're not eucalyptus. So in terms of genetic diversity, they add something. So David, you can buy me a beer later. Say thank you.
I think you can buy me a beer.
Eucalyptus grandis is kind of intermediate for everything, but that's good because it means we can hybridize it with lots of stuff, and we can probably find clones within the hybrids that we will like. And Eucalyptus globulus, it's really got great wood for just about everything. So hooray, hooray for the Tasmanian blue gum. So, and I'll stop there.
Thanks, Gary. A very interesting look at what Camcor is doing across a range of countries and range of species. Any questions? Okay. Thanks again. And next we'll... sorry, Justin.
How many new sites is Camcor moving to? Are you sort of settled on your locations, or do you have new partners and new locations?
Well, we are always interested in new members. Over the past 2 years, we've picked up 3 members in Indonesia. So that's definitely a new location and some very different kinds of environments. What we would really like to do is to build up our membership in some of these zones, because we feel like the more members we have in a zone, then we can start to leverage each other's work and share genetic material a lot more easily than we can across international borders.
Okay, thanks again, Gary. Next, Mike.
Thanks, Greg. So I'll be talking about genotype by environment interactions for Eucalyptus dunnii, just looking at the growth traits. So what I'm presenting today are the preliminary results from the first research chapter of my PhD, which is a collaboration between the University of Queensland and Seed Energy. And we also have a lot of international collaborators, which wouldn't be possible without them. So Eucalyptus dunnii, Gary already mentioned a little bit. It's warmer climate species, commonly used for pulpwood. It's got a limited natural distribution on the border of Queensland and New South Wales, a bit inland, and also inland from Coffs Harbour. So commercially as a pulpwood species, it's deployed in areas, warmer climate, where species such as grandis, the frosts are too detrimental for them. But dunnii survives. So Seed Energy, you've heard a little bit about already. They're a tree improvement and seed producing company based here in Tasmania and South Australia. And so they have a genetic improvement program for Eucalyptus dunnii. And Seed Energy, being based in Australia, preferably they'd want to do everything from Australia, so assess the trials, make selections and produce the seed, all from here in Australia. But most of the deployment is to international environments. So there's a bit of a question of, can Seed Energy do it all here from Australia, make these selections, while accurately predicting how these seed lots they select perform in other environments around the world? So the aim of my study is to evaluate the stability of these seed lots across different environments to inform Seed Energy's selection and deployment strategy. So we've got sort of 3 typical scenarios that come from this. So doing selection, if you look at the left graph here, if we select in one environment and then deploy into others that are higher productivity and there's no G by E, we're just going to see that the best is the best everywhere and it's easy. You can pick in one environment, it's going to be great everywhere. But if we're getting some genotype by environment interactions, see on the right here, what we select in one is the best, may not be the best in others, so the best strategy there is to pick the winners for each environment. But the problem with that is you need environments to be repeatable and then predictable from that. And so if they're not, perhaps you need to look at this seed lot here, C, which is stable across all, performs well, but it's not as responsive, it's the safe option. So Seed Energy has collaborated with multiple companies worldwide, establishing trials. So we've got 17 trials across 5 countries, and the majority of the deployment of dunnii from Seed Energy goes into Uruguay. So fortunately we've got a lot more trials there, and that's been the focus. And you can see here 1 to 8 are all in western Uruguay, which is their main deployment zone. And we've also got one trial in an atypical deployment zone down here near Montevideo. So the seed energy families, the 268 selected seed lots from the orchards, and these came from a native forest range-wide collection. This was put into a trial, and then selection done on that trial was culled into a seed orchard, and from this seed orchard, seed was deployed, established into trials in all 5 countries we've got down here. And then at the same time, it was also grafted into clonal seed orchards of Seed Energies. And seed from these were then put into further trials in Australia and Uruguay. And then, so that's one population of Seed Energies. And the other one was additional native forest families were put into one of the trials here, which was then culled in Australia after selection and turned into a seedling seed orchard. And families from this, from the native forest, put into trials as well. So these 268 families derived from these 2 populations. And also in these trials as well, we have some native forest seed lots and bulk lots. In Uruguay, there's some operational clones to compare against, and there's also some other seed orchard bulk seed lots. So overview of the trials. On the diagonal here, we've got the number of families in each trial. And then on the off diagonals, we have the families, the seed lots in common between the trials. So you can see there's quite a bit of genetic linkage between the trials, and these are almost exclusively seed energy families, which is what we're trying to look at. So for the data, we managed to, on all 17 trials, we managed to get assessments for diameter, breast height, and tree height. And we got multiple assessments on 8 of these trials. So if unlike this, we're going to call these the core trials, and we'll look at those in a bit more depth because we have these multiple assessments. And we've divided the assessments into 2 age classes. So we've got younger than age 3, sort of all of these here, and then we've got younger than 6 or older than 3 years. So Jarnier rotation age is about 12, and typically selection is done at around half rotation age 6. So we're sort of looking at normal selection age and earlier selection age as well. And so that data set, if we go back to it actually, so it's not perfect, there's different ages assessed at different trials in different locations. So we're going to use a multivariate mixed model to analyse it using ASRMLR, and we modelled each dimension of the seed lot covariance matrix as a unique combination of trial, trait and age. So up here we've got each trial for each trait at each age, that's a unique ID, and we're comparing all these unique IDs against each other. And then we used a first order factor analytical structure for the seed lot effects. And we're using this to estimate the repeatability of these seed lots for each of these unique combinations. And then we're going to look at the G by E by looking at the correlations of seed lots between these unique combinations. So if we just look at the means for diameter, breast height and height, see they follow a fairly expected linear trend. As age increases, they increase, and is pretty consistent across trials for both DBH and height. And you can see that with the lower productivity, the curve's already a bit lower, such as China, but otherwise nothing too out of the ordinary. And then if you start looking at the correlations, so we start with just those core trials where we have the multiple assessments. At the top here, we get a matrix of correlations between each of these assessments. And then we've simplified it a bit by looking at the average of these down the bottom here. So in these trials, we've got younger than 3 years, older than 3 years in those 2 age classes. And straight away you can see from the averages that overall the correlations are quite strong. And also importantly is that between the 2 age classes, there isn't much difference. So we're not seeing much increase in those correlations from younger than 3 to older than 3 years. And then if we add in the other assessments, so not just looking at the core trials, these underlying ones, but all the assessments we have of diameter, you can see that still correlations are still quite high. And with each of these ones, we're looking at their average correlation back with those core trials. And same again, there's a bit of a difference in age, but not much. And then the repeatability, and so it's quite low, it's just for diameter at breast height. And same again, we're not looking at seeing much change between ages. And then if we look at height for the same thing, we start with just the core trials again. We've got the model assessments. Same again, we've got pretty strong correlations here for both age classes. A bit more of a difference between them, but we're still going from, I think it's 0.83 to 0.91. So strong correlations all over. And to look at it again, if we add in the additional assessments of height for all the other trials across countries, there's a little bit more variability, but overall, still getting strong correlations. And same again, between ages, there's not much difference, little improvement. And repeatability, similar scale to height, to DBH, fairly low, but consistent. And this one, almost no difference between the age classes. So then on those trials where we had multiple assessments, we look at the correlation between the ages of the assessments, and you can see for both diameter at breast height and overall tree height, really strong correlations. So we're not getting much change from that earlier age class, from younger than 3 years to older than 3 years. And you can see there's some slight outliers. We've got the Spain trial, 0.62. This trial was the only trial that wasn't specifically for pulpwood. It was actually a biofuel trial. So it's the only trial out of these that is irrigated, fully irrigated. All the others are just rain-fed. So potentially what we're seeing there is a bit of an influence of treatment. But that's all we can say at this stage. And then the other one, Uruguay 9, 0.69, 0.79, still strong correlations, but a bit lower than what we've seen everywhere else. And that's this trial down here, out in the atypical deployment zone. So potentially there's something happening there. We're getting a bit of interaction when it's out of its normal range. I think I went pretty quick through that. So, to summarise what we've seen, these correlations are quite strong across diameter at breast height and height. So this is indicating we've got low GBE across, we've got 5 countries here, and we're seeing low genotype by environment interactions for growth traits. And we also had a bit of an opportunity to look at assessment age. So we saw there was a small increase in the correlations between these 2 age classes, indicating there's little but some benefit in waiting until age 6, half rotation age, to actually assess and select from these. And to tie this all back into seed energies question, is that from these results we can see that it's suggesting that selecting one environment and then deploying it to others, the performance is fairly stable, and the best seed lots in one location are likely to be the best seed lots in other locations. That's the end. Additional acknowledgements, I don't need to list them all out, but yeah, a lot of international companies have helped out with this and wouldn't have been possible without them. Thank you.
Now, I've spent 5 years grappling with G by E, so I could spend 5 hours talking to Michael, but we'll leave it open to other people to ask some questions about G by E in WA.
I'm surprised that you don't see more G by E. Do you think you had enough power, or
A lot of trials and a lot of trees in
is
there.
there? Is there a wide enough variety, or
Potentially, I mean, particularly between, well, within Uruguay, they're all in that deployment zone, so this is where it's already been shown to grow well. And there is a bit of a north and south difference in temperature and rainfall, but you're still planting it where it grows well. And perhaps that's part of what we're seeing with Spain, which is not really where they deploy it for pulpwood, and kind of confounded by the irrigation, but perhaps we're seeing some interaction there. And you can't really draw too much out of having just the one trial in one country on the other side of the world. So more trials may help.
Any information on the flowering in the seed orchards and how that might have affected the rankings? There is an argument within OB families that the best, the most outcrossed families will do best everywhere, which tends to mask the G by E when you're dealing with, when you remove that selfing, variable selfing effect. The seed orchards flowered well?
Yeah, well, it's a bit of a question because these were planted a while ago, but particularly we've got 2 different pollen clouds there from the early trials and the later trials, so there could be something going on there. But yeah, we're putting in more trials still with new seed from new crops, because now those seed orchards are flowering really well and really high production. But it definitely would have been different 10, 15 years ago when the seed was collected. So that's just an advocate for putting in more trials and continuing to test.
Rose.
I might be wrong about this, but I think Dunedin has a relatively restricted native distribution.
I showed that on the
Yeah.
second slide, just that little bit inland.
So do you know if other species that have similar restricted distributions also show low devalue?
I'm not sure about that. Straight up, I can't. I haven't thought about that too much.
Okay, thanks again. And our next speaker is David Lee, so we're back to the tried and tested of the old fellas.
Old fellas, hey? Let's see, I don't think I'm quite as old as you, and one of the things with this is that if we look back 20 years, would anybody have been talking about Crimbias other than I? That's a question I've got here, but in this talk fest that we've had here, I think there's probably been about 10 presentations that have actually talked about Crimbias, and I think that's an indication that it's actually a group of species that's gaining importance around the world, and it really is something that I've been harping on for the last 20 years, and it's good to see that there's 55,000 hectares in Brazil, and in South Africa, as I'm going to talk shortly, they're actually predicting that out of the high KwaZulu-Natal coastal area, that most of that area will actually go under Crimbias. So I've got a couple of different authors here. Just thought to quickly introduce the species. It's been run over very quickly, but we've got Trelliana, got Citriodora, which actually goes from Cooktown down to just south of Townsville, then a bit of an integrate or disjunct zone down to Maryborough, out to Carnarvon Gorge, 600 kilometres inland. Talking about huge scale here. You've got a zone where you've got intergrades with Variegata, and then Variegata goes all the way down to now Taree, and that's because of some stuff that Merv did. I thought I'd better throw in some molecular genetics. So there's been, up in the north, we've got some chloroplast capture. Down the south, we've got chloroplast capture occurring. Henry I seems that, initially Rachel King, in her PhD, found that it seemed to be a species that was under some sort of selection with isozymes. We start looking at it from a microsat point of view. It seems to be complete gene flow between Variegata and Henry I. So what's going on? There's a whole lot of questions there that still remain to be answered. And then Adam seen chloroplast capture between Trelliana and Citriodora in North Queensland. So you've got whole lots of different reticulate evolution going on. Now, just summarising some of the results we've had from the past, got reasonable heritability in Variegata. Convallaria, see it's raised its ugly head in West Australia. We first detected in 97, and we've got heritabilities in the order of 0.44, and craft pulp yield, heritable, highly heritable, or moderately heritable across a range of different trials. And I guess one thing, Mike, we've actually got 25 hectares of progeny trials out there, so it's a species in waiting, but it's also a species that we maybe taken it a little bit further.
Good.
Looked at myrtle rust resistance and showing from a immune hypersensitive reaction, and then these are the three classes where you'd actually have susceptibility. And again, within this is across the Crimbias species and hybrids, heritability order of 0.3, and so we've got some moderate heritability that we actually can select for myrtle rust. Now, background for the current study. They're really developing around the world, and there's more and more interest, and we've heard about that. We've been working on it for about 22 years in Queensland, and one of the things, the pure species can't be propagated vegetatively, and that's a real holdback for a lot of the countries overseas where you can't actually go ahead with this. So you actually have to have looking at hybrids. And in Queensland, 80% of the timber that goes over the saw bench from the native forest is spotted gum. It's also the #1 pole species for Northern Australia, and it's designed. And you know, you saw the form in the previous slide, which is actually showing the form of the spotted gums. They've got magnificent form. We don't actually have to do much selection for form. And you know, we've done a study across the whole of Northern Australia, along the east coast, down to northern New South Wales, and we did it by Bureau of Meteorology forecasting zones. In 8 of the 10 zones, spotted gums as a group were in the top couple across. So it's a huge spectrum, and we're talking about from higher rainfall zone areas, 1,500 millimetres, down to 600 millimetre type rainfall, and a whole range of different soil environments, including environments that you wouldn't actually normally expect to have them. So from red soils through to cracking clays, and it's performed across all those different environments. And so it's the best option in Northern Australia from a hardwood point of view. And I guess we've all had that alluded to us, international interest in it in hotter, drier, tropical and subtropical environments. In South Africa, 20% of the KwaZulu-Natal coastland is below 900 millimetres, and that's actually expanding. That's the long-term average, and there's also increase in pest and disease. Leptocybe, Thamassocories, Gniptera are really hitting the eucalypt plantations over there, and they're really getting quite worried. Also, they've had a whole lot of droughts over the last few years, and so that's sort of led to actually substantial plantation death in the KwaZulu-Natal coast. And so, in collaboration with ICFR, I've established a group of new trials in South Africa with Carimbia hybrids that we've developed and bred in Queensland. Just looking at where the trials are, that's Richards Bay, that's Durban there, and they're both basically north of Richards Bay, so SGE 49 and SGE 50. And when we start looking at it, I just decided actually for this study just include 3 trials in Queensland that had a reasonable overlap with the germplasm we sent over to South Africa. And so we've got a trial 458A, which is from north of Rockhampton, so above the Tropic of Capricorn. 458C, which is basically west of Gympie, so Gympie would be in there. Brisbane here, and you can see corresponding, between 28 and 29 degrees south in South Africa, and only about 30 kilometres separation between them. And then had another trial down here, 458D, down to Grafton in northern New South Wales. So trying to actually make sure that we covered the full range of environments that they might be subject to in Africa. And just a little bit of information about them. So a lot more genetics, more families in the trials in Australia. Just send over 28 seed lots, all control cross of that. And one of the things with the trials in Australia, I don't need to test anymore whether it's Carimbias are the best thing. We've put the benchmark there, so we actually just put out progeny trials. Whereas in South Africa, they'll tax the progeny trials. They've got control of the commercial clones and also the material that's actually the most promising material under selection in South Africa. And we use Bayesian statistics in R, and basically I'll just jump straight into the results because I'm conscious that everybody probably wants afternoon tea. Just looking at the Australian trials. One of the things with the trials, Australian trials with age 3, unfortunately the industry didn't have money at age 3, so we've got age 4 results to compare and contrast with. With the trial furthest north, so this is 458A, and Variegata here, and I've got box plots, and I've decided to actually provide all the information. And so what we've got is we've got actually underlying that we've got family structure but by just showing the box plot, which actually has the mean and the bulk of the population, and then showing full spread. And we've got normal curves for all of this material. So variegata, this curve here, about 9.6. In this, we've actually got Henryi and Trelliana by Henryi hybrids, shown over in this box plot over here on the right, actually at age 3, 12 centimetres diameter. So you're talking about reasonable growth rates, and it was actually pretty close to average rain. That's the mean for both of those. When we're looking at the lower rainfall, the red soils here, west of Gympie, and here, variegata, average 6.5. The best of the hybrids was Henryi at 7.3. And people might say, why have you actually got a lot more variegata hybrids and a lot fewer Henryi hybrids in the whole thing? That actually goes back to the history. Back in '97, put in progeny trials, and Quambularia absolutely creamed the Henryi trials, and we had variegata trials next door, and we had families and provenances that were showing much higher levels of resistance or tolerance to the disease. Is that me?
Yep.
Okay. 5 minutes, good. I might get there. Well, I might keep you in. And we've got similar results. One other thing that's actually, I just thought I'd chuck in there, is we've actually got Trelliana by Tesselaris hybrids. And we actually have been considering this as something that actually might go into very sodic type soils. In South Africa, looking here, we've got, I'm presenting it in two ways. One with the controls, local controls, and then next slide will be without the local controls, just focusing in on the Crimbia species and hybrids. So Henryi 9.3, Crimbia hybrids as a whole average 10, and the best of the local controls were up around 8.8. And so you're talking about here, this is Grandis cam, a couple of different clones from South Africa that were actually selected for that particular environment. Here, Grandis Europhila, similarly selected for that particular environment, and Longia Strata is another environment. So at the moment, they're moving towards Henryi. They can't propagate it, and that's why they're actually interested in looking at the hybrids. Similar story when we go to the other trial, higher rainfall, and the Henryi 10.6, mean of the hybrids 11.5, and the best of the commercial clones about 10.3 at age 4. We'll start looking at drilling down a bit further, looking at the Citriodora 10.7, and as from the previous slide, Henryi was 9.3 centimetres, and Trelliana by Henryi 10.1. So we've got sort of similar story that on average the hybrids are doing better. And when you actually start considering that they want to actually start deploying some of this material, and at both a family level, if I went down and showed you actually at a family level, there'd be families up there that they could deploy that actually be much higher, and then there's clones that are also much higher as well. And I guess this is what really they're facing over in South Africa, over in this area. This is a GC hybrid here, a clone, and basically it's been defoliated to a large extent by all the pests that they've got. And here is showing Henryi, and that's the reason they've actually started to move to Henryi. Here is actually, on this side, we've got a GU clone. Just thought I'd actually look at the genetic parameters, and with this, basically, within this trial, we had low heritability for diameter, and within the Australian trials, we actually had moderate to high heritability for diameter growth. And when we look at the genetic correlation between them, it's actually pretty good. If I was actually, and that's just a bivariate within trial, between height and diameter. If we actually start look at between the trials, and this is looking at Australia versus South Africa, here, heritabilities are intermediate when we start combining all the trials, and South Africa has gone down. Genetic correlation across sites for all of trials combined, when we've got trial and rep included in the analysis, it was very high for for diameter. It actually went down about 0.5 when we actually looked at the height. But if I actually drop out the trial down at Grafton, it went back up. The Grafton trial is actually subjected to a lot of frosts. So, where to from here? We're expanding the trial network in South Africa, Brazil, Malaysia and Laos. We're looking at individual trait heritabilities from low in South Africa to moderate to high in some of the Australian trials. And really high genetic correlation between the Australian and South African trials. Now, one of the things, if we actually look back at the past, we've got a whole lot of germplasm from South Africa, which I tested for Dunnii, Cluisiana, Grandis, and anything I've introduced back into Australia from South Africa performed at the best, as only as good as the best of the Australian, and most of the time it actually performed more poorly. But we can actually select material here, they'll perform better in South Africa, it appears. And so they're performing well in South Africa and outperforming locally developed species and hybrids at the moment for that particular region. And so there's opportunities for clonal deployment and deployment of elite families as well, based on these results. Thank you.
Okay, we have time for one quick question.
The difference in heritabilities in Australia and South Africa.
Yep.
Do you know are the genetic variances similar, or like so is this an increase in environmental variance or a decrease in?
We haven't actually looked into that at the moment for these particular trials.
A high correlation.
There was a very high correlation. Probably part of it is the fact that we actually got a very limited number of families in South Africa that we're looking at compared to what we had in Australia.
Because if you've got really low variance in one of the populations, the correlation is going to be high just mathematically. Anyway.
Yeah, that's right. And they're things to look at in the future.
Okay, thank you, ladies and gentlemen. If you could resume your seats, please. I'm still the same person I was before, and the session is the same as it was, genetic improvement. So we've heard in the last few days a lot about genomics and species and provenance level information. The last session, I think, genomics didn't get a mention other than obliquely. So now in the next section, we're bringing it back together. How can we use this genomic information in moving to the next stage in using in breeding? So my colleague Richard will take the stand.
Thanks, Greg. Yes, I'm Richard. I'd like to single out two of my colleagues. One is Josky, who you all know, as well as being a wonderful, I was going to say quantitative, molecular geneticist. He's the only molecular geneticist I know that loves the mixed model equations as much as I do. And also I'd like to single out Vincent Borner. Now he's a frighteningly, scaringly brilliant geneticist who's a recent import from Germany into AGBU, the Animal Genetics and Breeding Unit. So this project, it's been great to get to know Vincent. All right, so I'd start with this message, breeding is applied economics. I was thinking cheekily of saying economics. Now, the current director of AGBU actually got up at a forestry conference one day and said this, and I sort of didn't get it at the time. I think surely breeding's more biological. It's producing, crossing things and producing seed and germinating them and raising young plantlets in the nursery and then getting them established in trials. But then I thought about it, well, yeah, maybe he had a point. What are we trying to do? We're trying to predict an economic circumstance 30 years into the future. And we're saying to a forest grower or a forest processor, hey, we can deliver you improved genetic material that will lift your profitability. And that's quite a significant claim. It's quite a bold claim, isn't it? You know? And so when we look at a tree, we tend to see dollar signs. And I feel somewhat grubby saying that, knowing that there's so many noted ecologists in the audience. But it's in reality.
What was the price of the geneticist?
Yeah, good point. This bugger's always too quick. He's too quick. And I apologise, Brad. I when you see a gum tree, you probably don't see dollar signs, so you shouldn't be up there. But it is true. We look at dollar signs and how is a tree going to make a forest grower more profitable? So at the STBA, we're known as data hoarders. We love data. We'll use any kind of data as long as it's useful. And that's always been our philosophy. So how do we select for profit? Well, we select on the basis of genetic values, namely the estimated breeding value. So on the left-hand side here, we have a category of traits called selection criteria traits. These are traits measured in the field. We partition growth according to site type, like the green triangle or Tasmania, and also according to age. These are things measured in the field. We take cores, measure density, we take pilo measurements, predicted pulp yield on the core, stem straightness, myrtle rust resistance. Now we move to the right a bit, and we have these class of traits called breeding objective traits. Now these are traits that directly affect profit. We don't particularly want to inherently interested in growth in the green triangle at less than 5. We're interested in improving volume, harvest age volume on a per hectare basis. We're interested in whole tree density, not just core density, whole tree kraft pulp yield. So these are things that directly affect profit. Lastly, over on the right, we condense all the breeding objective traits into a single aggregated value called the dollar index value. And we do that by using economic weights, which are computed independent of genetics using a bioeconomic model. All right, so that's the process for getting a dollar index value or getting a dollar value on that tree. And it's really important getting that dollar value right. You know, I know retirement's 30 years, maybe 20 or so years into the future, and I could be well and truly retired, but I had nightmares of someone knocking on my door saying, "You were wrong. That dollar was not right." All right, David. So at the STBA, we have a genetic analysis engine that integrates information from a variety of sources. So in the case of the national globulus analysis, we have 18 selection criteria that we fit into the model. And these have been measured over a network of 158 trials. Each trial has a different heritability that's accounted for. We have different design features that we need to account for. These criteria have been measured on over 300,000 genotypes spread across 3 generations. Those genotypes descend from 8,000 founders that are structured into 18 genetic groups. We have a range of family structures, OP families, CP families, bulks. And our breeding program we've been aiming over the last decade to keep that breeding population constant in terms of its effective size at around 200. This is so we can balance long-term gain with diversity. And currently we account for relationships between measures by using the pedigree relationship matrix and trait correlation matrices at the genetic design effect and residual levels. So we gather all the sources of information and we collect them into a huge system of simultaneous equations. In the case of globulus, it's about 15 million, which by our standards is quite a small one. For our Swedish client, I think it's 250 million. But thanks to Vincent's great new solver, it's no big deal for us. It's maybe an hour or two, or even for globulus, it's probably 20 minutes. Right, so what is single-step BLUP? I'm going to cop out and not show equations, which is rare for me because people that know me know my proclivity to show equations. But it's essentially BLUP, best linear unbiased prediction, with a bit of G thrown in. So what do I mean by bit of G? Well, our regular pedigree relationship matrix is of the dimension 300,000. That's the number of genotypes. And potentially the G matrix is also of that same dimension. But we don't genotype everything in the pedigree. At the moment, we have about a 3,000 size G. So I call it a 1% G, given that it's 1% of the 300,000 of our total pedigree. And we particularly like single-step BLUP because it aligns with our philosophy. We think genomics is just another source of information that we must use. And I particularly like it because our operational breeders do not have to adjust their strategies too much. I've got a picture there of an operational breeder being given a list of GBVs that have, maybe from 2-step selection, genetic selection, and he scratches his head and, well, how am I going to use these? But with single-step BLUP, the elegance of it means that they don't have to worry about that anymore. feeds into the big machine, and they still select on dollar index values. And they do not have to calibrate disparate sources of information. I'm going to talk about results, but unfortunately I've got one equation there, accuracies. Accuracies are great things because that's how we can benchmark the addition of new information. Will the new information increase accuracy, or will it decrease accuracy? We could get garbage in, so it will decrease accuracy. So accuracy is defined as the correlation between the predicted variable and its true variable, in this case the EBV and the true breeding value. And I've got a horrible looking thing up here in the numerator, the expected squared deviation of the predicted variable from its expected value. And that's the definition of variance. So we call this the sampling prediction error variance. And we want this to be as small as possible, in fact 0, because you want u hat minus u to be 0. If its prediction error variance is 0, accuracy is 1. Now theoretically, if you had no information on an individual, the expected prediction error variance will be approximate var, the true variance, and you'll get an accuracy of 0. So accuracies range between 0 and 1. Now, we've got a new method to derive these prediction error variances based on Gibbs sampling, and we're just test driving it at the moment, and it's very computationally intensive. I haven't really finished getting all the results for the full production run, so I had to revert to using a cut-down version of the full national analysis. And I decided on using 5 base generation trials in Tasmania here and 1 second generation CP progeny trial. So when we began this project, we thought, well, we had 2 hypotheses we wanted to explore and demonstrate that they were true. One, we'll get a one-off boost in genetic value accuracy. So I have here 2 plots, and each dot on these plots represents the accuracy of the tree, its EBV accuracy, generated on the y-axis with genomics and on the x-axis without genomics. And you can immediately see that all the points are above the 1-to-1 line, so there's been an improvement in accuracy with genomics. Now, I've probably skipped ahead to results, and I haven't even spoken at all about how I constructed the G matrix. That is a seminar in itself, so I've just skipped over that. I got all the lovely read depth data from Josky, and I converted that to a G matrix. So that's another seminar. The one on the left-hand side here are the accuracies of those 375 genotype trees, and the plot on the right are the accuracies for the non-genotyped trees. So you can see that there's been a lift in accuracy also for the non-genotyped trees. So this is great news for me. I think this is wonderful, that the information from 300, in this case 300 genotyped trees, propagates through to the rest of the pedigree, the remaining 3,000 odd trees. And this is for one of the breeding objective traits, Kraft pulp yield. And I've got in this slide also the other remaining breeding objective traits, volume in Australian-wide conditions, density and Kraft pulp yield. So the increase in accuracy of genotyped trees is probably less apparent for volume. It's already fairly high, of around between 0.8 and 0.9, but it definitely improves for density and Kraft pulp yield. So what is the bottom line is, does it improve the accuracy of our index? Because that is what we'd make selection decisions on. And it does. It flows right through to from the selection criteria level all the way through to the dollar index value. So we're getting a marked increase in accuracy for both genotyped and non-genotyped trees. Phew, I think that's great. I think we did it. What does the full production run look like? I'm only getting results out now, as of this morning, and I think the story is sort of holding up. Certainly for the now we have 3,000 genotyped trees, and we have over here 270,000 non-genotyped trees. So I think there has still an improvement in accuracy for non-genotyped trees. So it's still propagating through 300,000 genotypes in the pedigree. And I've colour-coded the different dots as to the category of tree, whether it's a parent or non-parent, or in what generation it belonged to. Generally, you have higher accuracies for parents than non-parents, because parents have progeny, which helps their accuracy. All right, hypothesis 2. The benefit of a single-step BLUP will be that we'll be able to predict Mendelian sampling terms for untested progeny. What the hell is a Mendelian sampling term? Well, it's pretty basic, really. The EBV for an individual is its mid-parent value. That's half the breeding value of the mum plus half EBV of the dad, so the average of mum and dad. Plus this symbol over here, which I've used the Greek letter phi, and that is the Mendelian sampling term. That represents the effect of the sampling of genes that gave rise to that unique individual, and it will differentiate it from all its full sibs. So this Mendelian sampling term can only be predicted if the tree's been phenotyped and or genotyped. Now, accuracy of an EBV is also a function of the accuracy of the mid-parent value and the accuracy of that prediction of Mendelian sampling. And I'm hoping that I can get a good accuracy of the Mendelian sampling. Generally, you can really only get a good estimate of Mendelian sampling through cloning, and that's, but we don't clone at the STBA, so hopefully genomics will give us that lift in accuracy. And we can then also test new progeny in the new families. So Josky mentioned rolling front breeding this morning, and I've got a very simplistic explanation of what rolling front breeding is. So I have calendar years going down the rows, and across columns I've got what I call crossing streams beginning each year. So in calendar year 1 we do crossing stream 1, we cross. Calendar year 2 we begin the second crossing stream. 2 years from crossing we plant. It takes time to germinate the seed and get the plantlet ready. And then after another 7 years, we're ready to assess and select. When a tree is selected, we clone it into the breeding arboretum. Once it's in the breeding arboretum, it then takes a further 4 to 5 years for it to become reproductively available. So there's a 14 span before when something, like say, born, and when it can then be used again as a parent itself. What we propose with genomic selection is when the plantlet is then put out into the field trial, it's only just a very small plantlet, we assay it at that point and do a tree plan run and get its index value, even though it hasn't been phenotyped, and it will be differentiated from all its full sibs. In fact, we can do within and between family selection and stick it straight into the arboretum without even testing it. And we still will attest it at after 6 or 7 years hence. So, to simulate untested progeny in that second generation CP trial that I had in the run, there were 365 genotypes or individuals that had their genotypes that were typed, and I had their phenotypes removed to simulate the scenario of having these untested progeny with no phenotypes. And you can see it, obviously there's a lift in accuracy of these untested new progeny. Now, I can't partition out what that lift in accuracy is due to. Is it due to the increase in accuracy of the mid-parent value, or the increase in accuracy due to the prediction of the Mendelian sampling term? I might have to ask Vincent. Hey, Vincent, can you partition that for me? Yeah. So again, Mendelian sampling effects, you can predict them for breeding objective traits and for the index. So the upcoming plans that we have is to roll out a low-cost assay, and I think we'll be using the new Euc 67K chip. I used all 850,000 SNPs that Josky gave me to compute my G matrix. So I think we'll remain with the industry standard of having approximately 800,000 SNPs, and it will be a requirement that this workhorse of an assay, this low-cost, low-density assay, will be imputed up to what we define as the industry standard of approximately 800,000 SNPs. And the plan will be to routinely assay a subset. I should have removed 20,000 because I don't know if it will be 20,000 because that's quite inexpensive, a big bill. New progeny each year. We'll use simulation to identify the optimal allocation of resources. How many new progeny should we assay each year? And also, not just in breeding, but the industry will have the option to assay forward selection candidates for deployment. A future plan will also be to operationalise single-step genomic selection in Pinus radiata and potentially southern pines. I think I've rushed through it a bit too quickly and I've got time to spare. Oh, you're going good. All right. So conclusions, genomic information can be seamlessly integrated. The marginal change in index reflects the value in adding genomic information. And we will have an industry standard assay that can be imputed up to from lower cost assays. It means that information does not become obsolete. We still have phenotypic data from the 1960s and we still use it. We don't want to get into the situation where genotyping today in 2019 and we have to lose that information because we haven't thought through how we can keep using that information into posterity. And lastly, and I think it's the most important for our breeders, single-step BLUP enables a non-disruptive transition to the use of genomic information. No unnecessary changes to the breeding strategy, but it will allow us to investigate new tactics. Okay.
Thanks, Richard. Don't go anywhere. Some burning questions.
G'day, Richard. It's always nice to come along and listen to your chat. You've got some great ideas. I guess I wanted to explore a little bit what I touched on over lunchtime is the applicability of a genomic relationship matrix, which I assume you're using, to a mixed mating system and accounting for the selves in the family, in the OP families, and inbreed depression in those families.
Well, I mean, genomic relationships will certainly indicate what's self and what you thought was self but actually isn't self. And that's the whole idea of it, is to target or to find how one individual shares genes with another, to find that quantity more precisely. That's how it all works. So it will just correct pedigree errors. What you think were half sibs may be full sibs. Inbreeding and depression, that's something that is we're thinking about now. It's a global effect. It's not something that's particular to a trial. We only tend to be, at this moment, estimating within trial design effects. But this idea of a global effect that affects everything independent of what trial it's from, that's something we're now putting into tree plan, and I'll keep you updated.
Thanks.
Richard, I think I heard you say that the field trial, progeny trial process will continue with this material while it's being archived and
yes,
and developed.
Yeah.
Will that testing program continue to be the same size as
I think so. I think phenotyping is important.
Yeah.
We won't reduce it at all. The model always needs to be retrained, and I think phenotyping, as we do now, will be our strategy for always retraining and keeping that model fresh. Yeah.
In the first data frame, you reported a subsample, say 365 with Tassie dominated. The patterns seem to be the same for the whole data frame. Do you think that increasing the data frame gave you more confidence in the results, or can you extrapolate from a smaller data frame as you did in the first instance?
When I actually did do the full analysis of all 300,000 genotypes, was there a difference? Certainly not in the those things that were genotyped. I noticed the massive points were certainly above the 1-to-1 line in the non-genotyped trees, and there's certainly a big mass also underneath. And I have to explore that. I think accuracy could possibly decrease because something that you thought was connected to a tree with lots of information, well, in fact, isn't that connected. So potentially a tree could decrease in accuracy with genomic information. I hope I answered your question.
Yeah, I did see that when you extrapolated from the 300 genotypes to the whole data frame. But then I think, if I recall, you actually had the last slide with the whole of the data set across the 3,000 genotypes, and then am I correct? Or
This one?
That's the genotype only. I guess
that's the knockouts. What I call.
We may let you guys arm wrestle over that after the session. Thanks again, Richard.
All right.
And our next speaker is Vala Tuma from Gondwana Genomics, and he'll be telling us some of the work they've been doing in a similar area.
Thanks, Greg. Okay. So just to give some background about the company. So Gondwana Genomics was formed in 2014 with a license from CSRO for a commercial application of marker technology in Eucalypts. The main focus of the company is to provide molecular marker services for application in tree breeding. Our services not only include genotyping, we guide the entire process of application of markers in tree breeding, from DNA isolation to data analysis and providing you with molecular breeding values. So for genotyping, we have developed a new genotyping method based on sequencing. This method can be used for genotyping large number of trait associated or specific markers across large number of samples in a cost-effective manner. So the way this method works is that we design probes that capture about 200 to 300 base pairs flanking the SNP that you want to genotype, and we sequence those captured fragments and generate genotypes from them. So as we capture 200 to 300 base pairs surrounding the SNP region, we identify more SNPs than the targeted SNPs, because within that 200 to 300 base pair regions, there will be more SNPs. So that means we end up genotyping more SNPs than we target. Because we are using small fragments which are targeted, we get very high coverage. This leads to high confidence genotype calls and also high repeatability. And another important feature of our technology is our marker panels are flexible. That is, we can add more markers. For example, if you have identified a SNP markers that are associated with a trait of your interest, such as disease resistance, we can add those markers to the existing marker panels and genotype along with other markers. And another feature of our technology is that DNA quality and quantity requirements are very minimal. We can use a single leaf sample to get the DNA, and even any dirty DNA also we can use for our genotyping. This is particularly important when you want to screen large number of seedlings when you apply an actual breeding program. So in seedlings you don't get much of leaf tissue, so we can use one leaf sample to get the DNA and do the genotyping. So another important development we have done is that we have developed high throughput methods to discover straight enriched markers. Using these markers, we develop marker panels. So each marker panel is designed to capture about 1,000 target SNPs. We have developed such marker panels for different species of eucalypts like Nitens, Globulus, Grandis, and Peleta. With each marker panel, which consists of about 1,000 probes, we genotype around 3,000 SNPs. This is because, as I said, we are capturing the regions surrounding the SNP, so that means within that region there will be more SNPs. So with one marker panel, we will genotype around 3,000 SNPs. By combining the different marker panels that are developed for different species, we can genotype more than 20,000 SNPs if that is required. And most important feature of our marker panels is that we can genotype any species within eucalyptus. We expect that our marker panels will work in Corymbia also, based on the high genomic sequence similarity between the two genes. So in the last 2 years, we have genotyped more than 25,000 samples using our technology, both within Australia as well as overseas. So coming to the application of markers in tree breeding, so where we apply the markers. The first step to apply the markers in tree breeding is in quality assurance, pedigree reconstruction, and marker-assisted selection. In quality assurance, markers are used for identifying and correcting for clonal and pedigree errors. In pedigree reconstructions, markers can be used for identification of full SIPs within OP families, and also to confirm and correct SIP and parentage of OP and CP families. So, of course, the main application of markers is in marker-aided selection using genomic selection. So, let's see some of the examples of these applications. So, this is a genomic relationship matrix. This is a heat map of the genomic relationship matrix. This is a pairwise genomic relationship matrix between these individuals. These are different clones or ramets of a clones. And the color coding, the blue color the blue color is the high relationship, and orange color indicates that the relationships are low relationships. The off diagonals are the pairwise relationships between the individuals, and the diagonals are they give an indication of inbreeding. For example, there are 4 individuals which have got high relationships among themselves because they are assumed to be they are ramets of a clone. So, using the genomic relationship matrix, we can confirm that they are the true ramets of a clone. However, these two ramets are supposed to be ramets of a clone. But our analysis shows low relationship between those two. That means that's a clonal error, that's an error. And this particular individual has got the high value here indicates that this particular individual is an inbred individual. So, and these 3 individuals are supposed to be unrelated individuals. But our analysis shows that they're all completely, they have high relationship. They are like ramets of a clone. That means we have identified a new clone. So this is how you can apply markers for identification of clonal errors. Similarly, we can use markers for identification of full SIPs from OP families. For example, this is one family, and this is a mother tree, and this mother tree shows high relationship with all the individuals. That means we can confirm this mother tree is a true mother. And also within this family there are 2 blocks of high relationships. These individuals are full SIPs. So there are 2 groups of full SIPs, that is they have the same mother but they have different fathers. Similarly, we can use the genomic relationship matrix to identify or correcting the parental errors. For example, in this family, these 2 are the assumed parents, but as we can see, there is very low relationship between these assumed parents with the rest of the individuals within the family. Because we have genotyped other parents, we could identify the true parents of this family from the genotyped individuals. So this is an example of identifying and correcting for parental errors. Similarly, we can use our marker panels in hybrid analysis. The PC analysis clearly separates the 3 pure species into 3 different clusters, and these are the Brasiana by Paletta hybrids, and they form a distinct cluster. So our marker panels can be used for hybrid analysis as well. So, but as I said, the important application of markers is in marker assisted selection. So one of the ways you can apply the marker, one of the ways you can use markers for making selections is using genomic selection. So genomic selection is predicting future performance of trees and making selections based on those predicted values. To assess the performance of genomic selection, you divide the population into a training population and a testing population. And you use the data of the phenotype and genotype data of the training population and develop a prediction model. And you apply that prediction model in the testing population to estimate molecular breeding values using only the genotype, only the marker data. Then you estimate the accuracy of those molecular breeding values by correlating the molecular breeding values with actual trait estimated breeding values. So the accuracy of genomic selection is influenced by two factors. One is the genomic relationships captured by the markers, and the other one is marker trait associations captured by the markers. When you apply genomic selection in a population consisting of large number of families, the accuracy of that genomic selection is mainly influenced by the genomic relationships captured by the markers. Whereas if you apply genomic selection within a large within a family, the accuracy of the genomic selection is influenced by the marker trait associations captured by the markers rather than by the genomic relationships captured by the markers, because within a family the differences in relationships between the individuals will be very small. So our marker panels are particularly useful for accuracy of within family, because our markers panels are enriched for the trait associated markers. So as I said, I mean, one of the main applications of genomic selections in tree breeding is identifying superior lines within families. With traditional methods, you can identify superior families, but to identify the superior individuals or superior seedlings within those top ranking families, in it is genomic selection. So there are many studies where they have used populations consisting of several families for estimating genomic selection and estimating the accuracy of genomic selection. And in all these studies, high accuracies were mainly due to the genome relationships captured by the markers, because they have used large number, several families. But there are not many studies where single large families are used for genomic selection. So we have done one small project in which we have tested the accuracy of within family genomic selection in two breeding populations of two of our industry partners. For this, we have used 10 families with about 50 individuals per family, and we have assessed 3 traits: volume, density, and pulp yield, which are very important in tree breeding. So for this, we have conducted 2 tests. In one test, we have used unrelated families for model training, as a training populations for developing the prediction model, and this model is used in the testing population to predict the performance of those 500 individuals from the 10 families. In the other test, we have used the data of the 25 trees from each families and estimated the molecular breeding values of the rest of the 25 individuals from each family. Then we have estimated the accuracy of those molecular breeding values by correlating molecular breeding values with trait adjusted data. And here are some of the results. So in all this, there is a big variation for between the families in the accuracies, and volume seems to have high accuracy compared to wood traits. Between the 2 tests, there is not much of a difference between accuracy for volume and this is pilodyne density. So between the 2 tests, there is no much of a difference between volume and in the accuracy of volume and pilodyne. However, there is a big increase in the accuracy for pulp yield when we have used the data of the 25 trees from each of the test family. So in summary, we have developed high throughput methods for developing marker panels that are enriched for different traits. Currently, we have marker panels available for different species of eucalypts. So we have developed a novel genotyping method to genotype large number of markers across large number of samples in a cost-effective manner. So as I said, the important feature of our method is we can use this method to genotype any species within eucalyptus, and high within family accuracies indicate the potential for selecting superior lines within the families. So these are sorry. Okay, so that's the end of my presentation anyway. Okay.
Thanks, Bala. We're just a few seconds over time, but I'm sure we'll have some indulgence. Any questions for Bala? Certainly an interesting contrast with what Richard's presenting and what Bala is presenting.
Yeah, I have one. If you were testing a species outside, say, outside the eucalypt range, with your within family test, how much of your accuracy is dependent on other framework or other information versus what you can do to say with a new species?
Yeah, I think so. I mean, for our within family tests, we have used only limited amount of information. But as Richard said, if we had used all the available information, those accuracies would will increase.
Okay, but in fact, if you were presented with a new species where that information, the other information didn't exist, you would still have quite a useful tool there, I think.
As long as we have some information from some other families, not necessarily the related families, but yes, as long as we have information from some other families. Yeah.
Thank you.
Any other questions? Okay. Thank you again, Bala. And thank you for all the speakers.
Hi everyone, I'm Ming, and this is my sequencing machine. So as you've all heard, we've been working on this through the conference, sequencing the more SBI that you just saw outside, that's endangered area. But before that, I'll give you a little bit of an introduction on how does this thing actually work. Essentially, it's called a nanopore sequencer because we run the DNA through a protein nanopore, measure the electrical signal across it, and generate this squiggle, and we convert that into the actual bases. In order to do kind of our standard kind of high quality preps, Renee sent us a couple of samples last week. We ran it through our kind of high yield prep, which does involve a lot more sample, and we usually call it a blender prep because we do literally run them through blenders. That gave us about 530,000 reads, 12 gigabase yield, with the longest read being 72 kilobase pairs. So that's not assembly, that's a single read representing an actual DNA fragment, 72,000 base pairs. We ran a quick assembly on it, 2,000 contigs, contig N50, 200 kilobase pairs, and 300 megabase pairs of the over 10K contigs. This is kind of the read length that you can expect to get from kind of the high quality preps. So clearly, if you're running on the standard kind of like Illumina preps, your read lengths are all going to be kind of like down on this first bin. But over here, we've got that somewhere between 9 and 18,000 base reads, and that's kind of the median. The quick prep that I did, so that's kind of like hole punch. We just kind of like hole punch it and grind it up, run that through the Kaizen DNeasy kit, and then run it through the nanopore provided rapid kit. So using about 2 leaves. So getting that from sample to the sequencer in around 4 hours. From that, we got about 25,000 reads. Overall yield, so that's 71 kilobase pairs with a mean read length of 2.8 thousand reads. Read N50, so not contig N50, there's the actual read N50, around 5,000. Yep, fine. So the longest read that we have, that's 36,000 bases, and we just quickly kind of ran this through standard NCBI BLAST, got homology to kind of the predicted through to disease resistance protein that's predicted from the Grandis genome, and you can kind of see how that matches up here. We did get quite a bit of microbial DNA as well. So that's about 4% of what we managed to classify, 20% eukaryotic microbes, 70% bacterial microbes, and even a couple of like viruses. Whether that's contamination or representing actual leaf microbiome members, that probably requires a little bit more analysis to flesh out. But because this actually sequences everything that's in the sample, that's why you're going to get some of that in there as well. But the actual tree grouping, so we don't actually have a more SBI in the database that we're using. This is a very small subset of some of the initial results that we're getting from a collection trip that we had to Dean's Arboretum. But you can see kind of all the top hits are kind of roughly in this group that we have. And that's it. And information like this can often be really important for conservation if you want to get more more provenances from a really wide genetic background. We've also got a little bit of kind of the other data. So we've got thermal cameras. I've apparently been told that we used to do this from airplanes, but now I carry a thermal camera in my back pocket. That's you guys in thermal. We've also got location. I happen to know exactly where this tree is, but if I didn't, I've also got geotagged photos of it. And we used some of that technique when we visited Dean's Arboretum. Although smartphone GPSs aren't often particularly accurate, we use a lot of photos to get kind of this high coverage and being able to like kind of average it out to use some of that to kind of set the bounds of where our sampling area was and a bit of the terrain as well. We've also done a bit of photogrammetry. They wouldn't let me fly my drones around here, but I did manage to get a little bit of the ground-based cover and got a little bit of the bottom tree trunk as a 3D full-color model. So yeah, that's the results that I've gotten. And so essentially we've got 4 hours sample to sequence start, and 40 more hours from sequence start to a whole bunch of really interesting and probably actionable results. Thank you very much.
Are there any questions? Heidi.
What's your experience with the error rate of the sequence?
We haven't really done too much calibration, and this also varies whether you're going to be doing a full assembly with it or if you're just using it for genotyping. Currently, some of the published error rates, you're looking at somewhere around 10% on the reads, but it can go up to 99% in assembly, because the more advanced assemblers, you're also looking at things like correcting for some of the systematic error that you have, and also taking into account the base modifications that are some of the information that's also in the raw signal. So you can get a pretty high, so you can make pretty good genome assemblies with this. It is still a little less accurate on the individual reads, but it's usually good enough for most purposes if you're just using the individual reads.
Joskin?
So if you're putting it to assembly, can you make a comment on the assembly process? And you've got this very rapid sample to data flow, which is awesome. But from my understanding, the assembly end is quite slow and very computationally intensive.
I've personally never done an assembly, but from the people who in my lab who do, as far as I can tell, the assemblies not a whole lot more computationally intensive than any other assembly that you do, and the results of that assembly tend to be of much higher quality just because you're getting these long reads. There is a little bit of systematic error, and we often do some of the Illumina sequencing to cover in for that. So a little bit of Illumina sequencing, a little bit of nanopore sequencing produces kind of the very best assemblies that we have.
Yeah, the end results are particularly accurate, but if you do some Illumina sequencing and you can use that to polish.
How long did your Meliadora assembly take?
Using Canoe, which is the best of the best long read assembler, we took about 40,000 hours to assemble.
What about the fast one?
The fast one, we used Flies. That took about 250 hours. But again, once again, you'd want to polish with short reads if they're available to increase your per base accuracy.
And then you distribute those hours across the supercomputers.
Yeah,
CPU and LTU reporting.
yeah. Across the NCI supercomputers, it took a month.
So with that assembly that we presented there, we started with Miniasim, which is the even faster one. That was 15 minutes on 16 CPUs at Smart. So you get what you pay for, but with very, very quickly diminishing returns.
Anybody else? Well, we might keep moving. Oh, sorry, Jacqueline.
Is it the maximum size, the maximum length you can obtain, or if you improve your extraction, you can get longer fragments?
You absolutely can get longer fragments if you improve your extraction. I believe the current world record for the longest nanopore read is about 2.8 megabases. The longest we've gotten is around 200 kilobases, and that's often just to do with the kinds of things that we just need to do with Eucalypts to get rid of secondary metabolites.
There is a trade-off. If you have more long reads, you get less reads with this. So you've got to be careful. If you want to go for the world record, you might get 50,000 reads. But if you go shorter, you might get 500,000 reads, and you get much more total data output.
Yeah, but for assembly of a genome, you have already short reads. It can be interesting to have a very long read.
Yeah.
Balance.
I think it's important to keep in mind that even for assembly, like the short reads in nanopore are still several orders of magnitude than what you'd get out of an Illumina read set.
Just maybe can finish with the biological slide where you compare it to Dean's currency creep. So it's kind of like what Brad was saying on the tour earlier, that these species are a kind of a continuum and part of a complex. So it's not that the DNA is going to identify exactly which of the 700 species this is. It's going to tell you which lineage or which complex you're part of, because every individual tree is quite distinct and hugely diverse. So this, I think, tells you which group or what complex you're in within a day or before. Yeah.
We might leave it there. So thank you, Ming, for that. So Professor Jim Reid from UTAS is now going to give us some concluding remarks.
Thanks, Paul. Thanks, everybody. Before I try to make some concluding remarks about what has been a very successful and very full conference, I probably should start by saying some thank yous to the people who actually made it occur, made it possible. And so first of all, clearly like to thank the organising committee, Rose Andrew, Beck Jones, Brad Potts, Paul Rimmer, Dot Steen and Renee Valancourt. Without their input, it clearly would not have happened. And so a very big thank you to all of them. I believe the idea for the conference came from Beck, Paul and Rose, the three youngsters of the group, and I guess they thought they'd like to showcase some of the real discoveries and progress that has been made since the similar conference was held back in 1999, as it was alluded to earlier, where Renee and the then CRC for Forestry put together a meeting to try to start this exploring the Eucalypt genome, and followed on by the 2004 meeting, which looked at ways in which that might be achieved. Clearly, that's now been achieved, as we heard from Xander on Monday. We've made excellent progress in that respect. The on-the-ground activity, Dot and Beck, have been heavily involved with the on-ground activity, designing the program, making it run smoothly and all those sorts of things. So I think they deserve a particular round of applause. There have been other people who have been involved, obviously, to make it run smoothly. Paul has run the audio-visual superbly. I've been to plenty of conferences where it's gone wrong, so thank you very much for making it work. Mario has done a lot of stuff behind the scenes that you probably haven't seen, but he's made a big involvement with tomorrow's field day, so thank you to him. And Rob, with his tour today of the Eucalypts and also the photography that he's been doing, so he's again made a big input, so thanks, Rob. Normally at conferences like this these days, we would outsource the on-the-ground, the in-detail organisation to somebody who charges us very large sums of money and effectively charges you very large sums of money to come along to conferences like this. That didn't happen this time. Beck took an enormous amount on herself over the last 12 months to try to make sure that the thing ran smoothly, it ran on time. So Beck, thank you very much, and come up and I'll give you a photograph. Thanks very much, Beck.
I stole the flowers off the table last night, so you really shouldn't have.
Conferences like this don't happen without support and people putting in some funding. And so I'd like to acknowledge the sponsors, Eucalypt Australia, who have been very generous in getting this together, and a couple of their representatives have been here through the conference, so thank you very much to them. The M. Potter Foundation, UTAS for the provision of the facilities, the ARC Centre for Forest Value for its support of staff working in this, Greening Australia, who will be involved with tomorrow's field trip and have been involved right through some of this work, and Gondwana Genomics for the prizes and the contributions that they've made to the success of the conference. So thank you to all of those organisations. The conference has highlighted how far work on Eucalypt Genomics has developed over the last nearly 30 years, since the first paper on Eucalypt DNA markers was published back in 1991. We spent a lot of time talking about how it could be done in 2004, and some of us in this audience actually put in for an ARC grant back at that time, and I think it was 2005, and we were asking for between $5 and $50 million to actually do the sequencing. No doubt we didn't get it, as we saw, but it's staggering to think that that's what we were asking for and thinking was what was necessary back then, and we've seen somebody sequence the genome during the course of the week. So the progress has been fantastic. It's been dramatic. It's hard to pick out highlights from what has been such a succession of excellent talks. We started off with comparative genomics. We heard about the Columbia genome, so it's a great outcome. We went through phylogenetics, conservation restoration genetics. We went through the genetics of complex traits, developmental issues this morning, and we've ended up talking about genetic improvement of plantation species and breeding. To me, perhaps the thing that has come out most from this conference is the rate of progress that we've made across all those areas that has been underpinned by the genome sequencing collaboration. And so really the major thing that has happened was that big international collaboration. It involved a large number of people across right around the world, and it has underpinned the development then in all of those specific areas. So I think that's a really great outcome, and Xander highlighted that on Monday himself. So the opportunities have opened up in a whole lot of areas for people to use that sequence. In many cases, I think we've heard that they confirmed ideas we had from more classical approaches. So, for example, the importance of pollen movement and hybridisation, the strong effect of selection in natural populations were things we alluded to. We've got them confirmed and reinforced with much better data from the genomic era. We've also answered, I think, some questions that have puzzled us for a very long period of time, and there are highlights there that most people will have. To me, one of them was the fact that we now know, or we think we know, where Angophora should be placed. It'll be interesting to see how the taxonomists take and use that information to modify the taxonomy as we know it of the genus or the genera. All I can say is I sincerely hope that the taxonomists actually think about how the public view eucalypts and take that into account in any revisions that they might happen to make. There's plenty of room underneath that classification for the detail that professional scientists need in their work, but we really do need to connect with the public about what we think eucalypts are, and they need to be able to understand it. I think it'll make it much more accessible for them. Another one that came to my interest was the Eucalyptus marginata. We thought we knew the genetic structure of that population and so on from using marker technologies, but Margaret's talk illustrated that if we go to the genomic level, we really can start to find some finer level in things that we thought, I think, had been worked on and people thought they knew the answers, but clearly the power of the new techniques has allowed new information to come forward. Then there have been the talks that have suggested perhaps where we should go and give us hope that we'll make it into the future. So we heard this morning about genomic data and how it could actually be used to aid breeding programs. And Richard went there this afternoon to suggest that we might be able to actually get there. But Peter Volker said to me after this morning's talk, before he heard Richard, well, the 1999 conference promised that we'd have that very soon. It has taken us a while to get to the stage where the genomic information is being used to aid the actual breeding and deployment programs, but it does look as though we're finally achieving it. I think another one to me about where we were going was talk this morning, I think it was, somebody indicated there are families of genes that were in all the woody families but weren't there in the other crops and the weeds. And I think that's really useful. As a developmental geneticist myself, it's really interesting to know that you're identifying genes that may actually allow you to understand what makes a tree and what gives it the particular characteristics that we haven't been able to fully understand up until this point in time. So I think we've reconfirmed a lot of what we've done. We've made a huge amount of progress, and the talks have been really good. And we've actually indicated that we are on the threshold of really understanding how trees develop and how genomics can be used to actually influence what's in the ground out there across the world. So that's all been great. In finishing, I'd like to hark back, if I can, just to something I said last night, because not everybody was at the dinner last night. And that was that I want to acknowledge the great contribution Brad Potts has made to this sort of area over the last 40 years and to our understanding of Eucalypt genetics. While he will undoubtedly continue to make a continuing contribution in that area, because I'm sure he'll be back at work at 9 o'clock tomorrow morning, no, probably 8 o'clock if he's going on the excursion. Today is his last formal day as an employee of the university. He will be with us as an adjunct professor and an honorary position into the future. So that is really great. I'm sure he's going to add to the 300 plus papers he's already published on the area. So Brad, we thank you for your contribution. We thank you for the connections you've made around the world and the fact that you've been involved in organising conferences like this and bringing people together and developing collaborations over that entire 40-year career. So congratulations. thank you all for attending and making this such a successful conference. Dot's prediction at the start of the conference that it would be an outstanding success, I think in this case isn't only a line that will be used back to the sponsors and our grant-giving bodies, but one that really actually did take place. So thank you all for making that making your contributions. And Beck, it's back to you for some housekeeping, I think. Just before we go, I thought I would show you a couple of photographs of Brad. His dress sense wasn't always as good as it is today. And there's a young Heidi, I think, hiding in the photograph. We're not allowed to do seed collecting like that anymore, are we, Brad? No, IHNS doesn't like it. That was a 1995 conference, I think the first of the Eucalypt conferences, a broader conference across all of genetics that we had in Hobart back in 1995, and some other likely lads who have grown older. That's the group that was involved with something I think that was mentioned this morning, and that was the tree for the Dot's chloroplast genome, I believe. Is that correct, Dot? I presume so. And Brad and his longtime colleague Renee doing some sampling more recently. So well done, Brad.